So they have only like 50% strength today. I don't know. Even statistics class didn't have this kind of attrition rate. I thought people would prefer to show up for this one. Um, let's. So how was the lab session yesterday? Yeah, yesterday you had a lab session, right? Oh, afternoon. Okay. Ah, I see. Okay. Yeah. So still statistics is the one to blame. Um, I so I was hoping that you know, having worked out some problems in linear regression, that would have helped understanding better. Are there any questions that you'd like me to address before we get started for the day? Um, I'm sorry. The other day you wanted to ask a question, but we were busy in a meeting, so we couldn't. Get is there anything that I can answer now before we get started? Oh, for the GNQ. Kind of late for for that now. Yeah, that might be. What do you think? Huh. Okay. Right. Right. So actually, a handout might be a good idea. I'm not sure how feasible it is, but what you should do is post this as a reminder on Piazza. So I mean, when the data scientists get a free time, they'll be able to at least attempt to make a handout and put that in the general resources. I think it might be a useful thing to do once so that even for next batches we can continue using that. Um, so just if you post it on Piazza, it'll be there as a reminder. Over right now, we might forget to get back to it. So just do post that on the Piazza. Okay, so let's get started. Today, the topic that we are going to be covering is logistic regression. Uh, so what we did in the previous two classes is essentially we talked about how one can use certain easy to measure quantities and try to forecast some hard to measure quantities. The hard to measure quantities that we were trying to forecast were analog values. It's not a class variable, but some analog numbers. Uh, we are trying to forecast things like, based on the age and experience, what would be the salary that person might be earn. That's the data one could try to forecast. Based on the person's credit history, based on the type of job, based on the type of salaries, based on the type of number of loans that he has, you can forecast what is the right amount of loan that can be approved for that particular person. So in each of those cases, we were using some easy to measure quantities to try and forecast one hard to measure quantity, which in that case was an analog number. Okay. What we are going to do today is talk about cases where the thing that you would like to forecast is a class variable. It's a it's a it's got a digital values of 0 or 1, or equivalently yes or no. So the kind of questions that might be addressed in this is that given the person's job description, given the person's salary, given that person's age, given that person's total loan amount that he already has, should we be giving him another loan or not? So is it a yes or a no kind of answer? So it's a logic variable that we are trying to predict. The kind of regression that addresses that is called as logistic regression. Okay, and the the philosophy of everything that we have done till now is this. We try to do some basic ideas and see if those basic ideas can be applied. We try to see how far we can push that basic idea and apply to more and more complicated concepts. We spent 2 full days talking about y equal to mx plus c. That's linear equation, right? We Since we invested so much of that resources, when we spent all of that time on the very first day, we didn't want to let go of all of that effort waste, and we tried to see if we could use the structure, the formalism that we have in trying to fit y equal to mx plus c to try and fit nonlinear patterns and nonlinear functionality. We talked about how to do that. We did, not transformations, nonlinear transformations. We talked about how any level polynomial fit can be handled with just the linear infrastructure, right? Now, today we're going to be talking about logistic regression, and our attitude is going to be still the same. Can we still use whatever formalism that we develop for linear regression to solve these problems? That's going to be our attitude with which we are going to apply, which we are going to tackle this, with which we are going to tackle this particular problem. Okay, so let's say you are given a data set where you have some person's income level, and it shows for this particular income level whether this person was a potential buyer for an expensive product. Okay, let's say let's talk about a house, right? So the way you find out whether, given this income level, whether this person is likely to buy a house or not, is that you look at the past data. You take the past data, you tabulate income levels of people and whether they bought a house or not. Using that data, let's see if we can apply some kind of regression idea to make forecast on in future when you see someone with this particular income level, is he a likely customer or not? Right? That's the way we've always been approaching. Use past data, and using that past data, we are hoping that we can predict what the outcome is going to be on the future. So here is one such data. You have income level of that particular person and of variety of people, and what's on y-axis is whether they made that purchase or not, right? What you're seeing, what this data is telling you is that people whose income level were low, they did not buy house, but as the income level increased, they bought the house, right? Now, here is a case where this particular data is a fake data. Where you see that there is a very clear demarcation, right? At this particular point, any income beyond this level, people are making this purchase decision. But real life data is never going to be that clean. What you're going to find is there are people who are at higher income levels who choose not to own the house, right? So you'll have more data points over here. And you will also have people with lower income level who have actually chosen to buy the house. In which case, the threshold at which you're going to switch from 0 to 1 is not all that clear, right? So given a new data point where you encounter a person with particular income level, and if you want to make a forecast as to whether he's going to buy or not, you don't know what threshold to apply for that particular person. Okay. Now, if this was a problem of regular regression, where you are trying to predict a class, instead of trying to predict a class variable, you are trying to predict an analog number. Then what you would have done is you would have taken the data and tried to fit a straight line through it, right? So a line like this, you would fit a straight line through that data. And then what you would do is you would say, let's say you are given a new person with some particular income level. You're going to find where that income level is going to be lying on this x-axis. You're going to read off the value from the straight line that you fitted. If the value of the straight line at that point is greater than 0.5, you're going to say that, oh, he belongs to class 1. If that value on the line is below 0.5, you might decide to say that he's going to fall in class 0, right? That's a reasonable way to approach this particular problem. You still use linear line to fit the existing data, but you interpret the output of the linear line as perhaps probability, where you say that the number, when the number is greater than 0.5, then that perhaps means that there is a greater than 50% chance that that guy is going to buy the house. And when that number is less than 0.5, then perhaps that person has less than 50% chance of buying the house, right? And this slope of the line is actually going to be determined by the distribution of the points that are over there, right? So that would be a reasonable way to solve this particular problem. However, it turns out that's not a satisfactory way. Why? Let's say our data set was like this. Okay. Previously, I was talking about this being the data set, and this would be therefore the best fit line. Let's say I add another point to the data set. This point is of a person who's got a very large income, and definitely this guy looks like he has a house. This particular addition of this particular point should not in any way impact your conclusions that you make from this region, right? Because this is a clear-cut case. Really, this is not adding much to your intelligence about where this threshold is. The points that determine where exactly the threshold is the points that are close to the boundary, right? So I'm adding one point over there, but if I do the best fit line now, suddenly the slope of the line is going to change. The changing of slope of the line here has a very dramatic impact, because the place where you have a 0.5 threshold is also going to change. So you might pick the new guy whose income level is here. Because of this one particular point, you might make him as class 0 instead of class 1 in the other, right? And that is deeply unsettling. The fact that when you're adding points whose class, which is beyond this boundary, where the classification is very clear for this kind of point, those points influence where exactly you might draw the threshold line, right? And that is deeply unsatisfactory about the idea of using linear regressions for doing this kind of task. Do you see what the problem is, right? So we need some other type of method to handle logistic, this logistic regression, where you are trying to forecast which class the particular person is going to lie in, right? Now, so essentially what we are saying is the linear regression slopes can be much larger than 1 or much smaller than 0, and hence the thresholding becomes a very difficult decision to make. And it really depends on the distribution of the points that are there, and points which are not difficult points to decide turn out to influence where exactly your threshold is, and that's not intuitively appealing. In addition, all the issues that we had, we made certain assumptions about when linear regressions can be applied, right? The error terms, we said it needs to be normally distributed. We talked about error terms being independent and error variances being heteroscedastic. All of those assumptions will be violated when you try to use linear regression for this particular case. Okay. So linear regression cannot be used to solve logistic regression problems. At least it cannot be used directly. Okay. Now, linear regressions, the particular method through which we arrived at coefficients, the slope coefficients, is called as the least squares method. Okay. What we did was we computed the error, we computed the square summation of squared errors, and we found coefficients which minimize that sum of squared errors. Right? That was the least square method which we adopted for solving for coefficients in the linear regression. Logistic regression, there's a different method that is adopted, which is called as the maximum likelihood estimation. Okay. The method is different in the following way, right? The term likelihood, is often can be thought of as reverse of probability. We talked about several probability distributions, right? Binomial distribution, geometric, and Poisson, and so on. What those distributions gave you was that it allowed you to compute probability of some particular event given the value of parameters, right? The binomial distribution, the parameters that were involved were number of tosses and the probability of success, right? That's the parameters that were there. In Poisson, the lambda value, rate at which events were happening, that was a parameter. So given the parameter, what your probability distribution function did was it gave you a way to compute probability. What happens in this likelihood, maximum likelihood estimation, is sort of the reverse. Given that an event has happened, what is the chance that the parameter value is so much? Given the event, estimating parameter is the likelihood process. Okay. It's best to talk about this in the context of an example. So let's talk about an example. I'd have a coin, right? Possibly an unfair coin. I tossed a coin 100 times. I get 70 heads. What is the most likely value of probability of success? P. 0.7. What you have done is maximum likelihood estimate. Now, there is no guarantee that 0.7 is what the coin is exactly off by 0.7. That's not true. It is also possible that the coin was a fair coin with the probability of success being 0.5, and in that it is possible that you might have gotten 70 heads out of 100 tosses. That is possible, but it's highly unlikely. The most likely scenario is the head, the number of the probability of success is 0.7. That is probably the most likely scenario. What you did in your mind was maximum likelihood estimation. Given the data of the event, you are trying to get the estimate of the parameter that gave you that particular event. Let's talk about this with an Excel sheet just to make sure we all understand exactly what's happening. So what I have here is n tosses. In this case, I'm considering 10 tosses. Probability of success, let's say we are talking about a fair coin, the probability of success is 0.5. And what I'm giving you here is probability of R successes in 10 tosses. So probability of 0 success in 10 toss turns out to be this very small number. one success is this, two success is this. Which one would have the highest probability? 5, right? That has 24% chance. Okay. Um, Let me convince you that the formula that is there is doing what you expect. Well, I can't convince you. I don't think you can see what's there, but it's the NCR P to the power R Q to the power R formula that's encoded over there. Okay, this is the binomial probability distribution formula that's encoded there. So what you see here is the output of that. Now, what I am plotting here is R, let's say the number of successes that you saw in a given trial. You did 10 tosses and you actually see 7 heads. Okay. For that, we can compute what is the probability of that happening. What is the probability of that happening if for an unknown value of P. If P value is 0, the probability of getting 7 heads is 0. If the P value is 0.01, you can use the binomial distribution formula and compute what is the probability of getting 7 heads. Right? That's marked here. For different values of P, I am listing the probability of observing 7 heads. That's what is plotted here. Okay? Do you understand what I'm plotting here? Given that 7 heads has been observed, that event has happened. Now you are trying to estimate what might be the value of P which resulted in that. So in order to find that, what I'm doing is I'm listing different possible values of P. And I'm showing the probability. Given that particular value of P, how likely is this event could have happened? Okay? What I'm going to do is I'm going to pick the value of P that has the maximum probability. That is most likely the true value of probability for that particular coin. That's the approach I'm taking. That is not to say that I know for sure that that is the value of P for that coin. That is the value of P which gives me the maximum probability, the most likely value of P. Yeah. So if you look at this, what you see is that I'm plotting that particular probability. Okay. And that probability has a peak at 0.7. So the maximum likelihood value of P is 0.7, given that 7 heads were observed. Okay. What I'm ending up doing is maximum likelihood estimation. Is it clear what I'm trying to do? Given an event, I'm trying to compute the value of probability which would have resulted in that. And I say that the maximum likelihood value of P is the one that results in biggest probability. Now, lot of numerical algorithms traditionally were written, lot of these optimization problems were written with minimization in mind. Okay, just a traditional thing. Okay, people wrote algorithms which minimize some particular quantity. So what actually the R code does is, instead of phrasing it as a maximum likelihood, what they try to do is they solve a minimum likelihood problem by taking the log of this and instead taking negative log likelihood. So minimizing negative log likelihood is equivalent to maximizing likelihood. So the way our function is actually coded is in minimizing negative log likelihood, and that looks like this actually. If you plot the negative value of log of that probability, it looks like this. The minimum value still would give you, in this case, the minimum value is here. The minimum value would still be 0.7. Okay. Algorithmically, what is coded is minimization of negative log likelihood, but it's equivalent in principle to maximizing the likelihood. Okay, so instead of a least squares method, a maximum likelihood estimation method is used in the case of logistic regression. But what exactly are they maximizing? We'll talk about that in a second. Yeah. So here is what we are going to do. We are going to this is the problem we are trying to solve, right? We haven't yet specified how we are going to fix this issue of straight line. But we are going to take the following approach. The approach that we are going to take is, what would be ideal is if you have these set of points. If you have this set of points, instead of trying to fit it with a straight line, if we can fit with a sigmoid shaped curve, which is a curve that looks like this. If we fit this kind of curve, that will be a better description of the data, right? If we manage to fit the curve with this kind of, if you fit the data with this kind of curve, then adding further points here is not going to impact this threshold at all, right? This is a complicated curve to fit. This is a non-linear curve. We know how to fit only linear, right? So we are going to try and find out if there is a way to use the linear formalism to try and fit this. Okay, we'll get there. But obviously, when we try to fit, there are going to be some parameters involved. In the case of linear, what were the parameters involved? Slope and intercept. Two parameters were involved in fitting that particular thing. Even here, there are going to be parameters involved. Okay. It so happens in this case also there is two parameters involved, right? Now, the way we evaluated parameters there was how? How did we evaluate parameters in linear regression? Minimize the error, right? That method was called as least squares estimation, right? Minimum least squares estimation method is what we used, right? The method that is going to be used to evaluate parameters here is maximum likelihood estimation. What it's going to be a probabilistic estimate. You're going to say that what is the most likely value of parameter which is going to fit this data, right? That's what we are going to do. What I did just now is I've just defined to you, try to intuitively explain to you the term. What does maximum likelihood do? Maximum likelihood sounds like a fancy term, but it's what we do every day. When you do an experiment with tossing the coin 100 times and you get 60 heads, you're estimating the value of P from that experiment. What you're intuitively doing is a maximum likelihood estimate. You're not doing a least squares estimate. You're doing a maximum likelihood estimate. So this is the method that's going to be used to estimate parameters for this. It's hard to show that mathematics here. In the case of least squares regression, I was able to indicate to you how you compute the parameter, right? All you need to do is take partial derivative with respect to the slope parameter, take partial derivative with respect to intercept parameter, and I told you can compute it that way. That kind of computation is going to be hard to show for this. So instead, I'm appealing to your intuition, saying the way we evaluate parameters given certain instances or certain incidents and knowing the underlying probability distribution, the way you evaluate parameters, that method is called maximum likelihood estimation, and that's exactly what we are going to use to find parameters here, and that's what R does, right? We are not going to talk in detail about how exactly the coding is done. Yeah. I'll show you how we are going to compute the value. We are getting there in a second. All I did till now is define to you what is maximum likelihood estimate. Okay. So let's Go ahead and try to explain the idea of logistic regression using one concrete example. Okay. The concrete example that we are choosing is a simple data set. Um, an auto club mails a flyer to its members offering to send more information regarding a supplemental health insurance plan if the member returns the brief enclosed form. So there are, the US has this one very popular auto membership club called AAA, right? American Automobile Association. Uh, what they do is when you become a member of that, if your car gets stuck somewhere in the middle of the road, you can call that toll-free number, 800 number, and they will find a guy in whichever part of the country you are. They will find a guy who's near you, who comes to your location and either fixes the puncture or tows your car to a nearest garage. All of that for free. Right? All you need to do is buy membership into this auto club. Now, typically what organizations do is, when this is a huge club, AAA, I would say easily, 30-40% of all drivers are registered in AAA. So the huge membership data is there. Typically, when companies have that kind of data, they're always trying to cross sell. So their main product is this service of trying to provide. It's a kind of insurance. When you get a repair, they're providing you insurance, right? Effectively that. But they might also think that I have this huge set of members. Why not I offer health insurance as well, right? So in this case, that auto company is deciding, should we offer supplemental health insurance? And they send a notice to everyone saying that we are starting to offer supplemental health insurance. If you want supplemental health insurance, return this flyer back with your name and age and details, and, all that. Then we'll give you more information about health insurance, how to get the health supplemental health insurance. So that's what is happening. The auto company sent a bunch of flyers, and it's collected data about the age of the person who's returning and whether someone returned the flyer or not. That data. Can a model be used? Can a model be built to predict if a member will return the form or not? Okay. If you can build a model using some limited data, first you send it out to, maybe 5,000 people. 5,000 people, you find out how many people return. Using that, if you find the age characteristic of the person who's typically returning, then you know that, I have 10 million customers. If I can reduce the number of forms that I need to send based on the age of the guy who's typically returning, then that's money in my coffers, right? So using this limited data, can I predict the probability? Can I build a model for who might return the form and who might not return the form? That's the question that you have. Okay. So the data looks like this. You have, as you might expect, the people who are most likely interested in supplemental health insurance are people who are older. People who are younger generally they have this invincible feeling, so you don't get health insurance. That's what this data is showing you, right? 20-year-olds are not returning. Most 30 and early 40-year-olds also don't return. But as you start approaching, mid to late 40s, people start returning the forms. Okay, so you have this data, and you want to build a model that will fit this data, so that you can use this model to decide who to send the forms to and who not to send the forms to. That's the intent. And as I mentioned here, linear fit is inappropriate for it, right? We would ideally like to fit with a sigmoid shaped curve. And this curve would have continuous values. The curve does not have discrete values. The data had discrete values. This curve has continuous values. But I'm willing to live with it. Why? Because depending on the value, if the value is above 0.5, I can interpret this guy as a probability that the guy will return I can interpret this number as probability. So when the value is greater than 0.5, I can say that that guy is going to return the form. When the value is less than 0.5, I'm going to put him in this class saying that he won't return the form. Right? Of course, I'm choosing a threshold here, 0.5 as being a threshold. You can choose a different threshold. If you want to send these forms only to people who have greater than 90% chance of returning, you can set the threshold to be 0.9 and send the forms only to those guys. But that freedom is there with the business owner. You are just fitting it with a sigmoid shape curve. Okay, that's going to be our plan of action. This kind of curve, one commonly used functional form for that kind of curve is this. Okay, 1 over 1 plus e to the power minus x. If you plot that, that has this kind of form. Let's look at, let's see if we can understand the details of that equation. I'm writing the equation here. What's going to be the value of this function when x is 0? So let me use same notation there. It's written as mu. So I'm going to write this as mu. When mu is 0, what's the value? So this e to the power minus 0 is 1. So the denominator is 2. So it's 1/2. Right? So this function has a value 1/2 when this guy is 0. What happens when the value of mu becomes very large as it approaches infinity? As mu approaches infinity, this is e to the power minus mu, right? E to the power minus mu is 1 over e to the power mu, correct? So as mu approaches infinity, this ratio approaches 0. So this number approaches 0. So this function approaches 1. So as mu value increases, it approaches 1. What happens when mu value goes to minus infinity? When mu value goes to minus infinity, this is like e to the power infinity. So the denominator becomes large, infinity. So it's 1 over infinity that approaches 0. Okay. So this is a function that looks like this. It goes from 0 to 1. When mu is equal to 0, its value is exactly 0.5. Okay. Now, I can take this mu. I have this particular data. I want the value of 0.5 not at 0 but at some other value. Right? The way I accomplish that is say that mu is some beta naught plus beta 1 x1. This beta naught and beta 1 would move the curve enough to wherever you want. What I'm going to do is this. I'm going to find the value of beta naught and beta 1, which will be the best fit for this data. Best fit in what sense? Not in the least square sense. Best fit in the following sense, that given this data, what is the most likely values of these parameters? Okay, I'm going to ask R to estimate that. R will estimate these parameters, and that the way I'm going to interpret that is that's the most likely value of parameters given this data. Okay, these two parameters are there. What is the meaning of these two parameters? Well, one parameter is needed to move the curve to wherever you want the 0.5 threshold to be. Okay, the other value of parameter, effectively what it does is it controls the steepness of this curve. Okay, if this data is the threshold is very narrow and very clear exactly where the threshold is, then the steepness parameter will be very high. If the threshold is not very clear where it is, there's a lot of overlap, then the steepness parameter will make sure that the curve is like this. So two parameters are there. I haven't told you which parameter causes slope, which parameter causes the movement yet. We can figure it out a little bit later. But is the intent clear? What we are trying to do? We are trying to fit a sigmoid curve, and there are two parameters that are needed for this particular sigmoid curve. One parameter tells you where this line is. Should it be like this or should it be like this? That's what one parameter is deciding. The other parameter decides the steepness of the slope. Okay, given this particular threshold, should the curve be steep like this or should the curve be more like that? Okay, that's what those two parameters are deciding. And we'd like to fit this to this particular data. Problem is, we don't know how to do a nonlinear fit like that. The only fit that we know how to do is linear fit, right? Now, what did we do when we encountered a data which had nonlinear pattern? We found a transformation that will convert the data into linear. We are going to find exactly the same approach here. We are going to try and find a transformation which is going to convert this curve into a linear curve and fit it there, and then take it back, take the transformation back, and go back to the original problem. Okay. So before I do that, let me write this. So this particular function can be the same as this. Okay, I've just rewritten the terms. This mu would be beta naught plus beta 1 x1 in the case where you have only one predictor. Just like you had multiple linear regression, it is possible that you can have multiple predictors, and the multiple predictors case, that formula looks like this. That mu value is now written as beta 1 plus x1 plus beta 2 times x2, so on and so forth. The complexity of the problem does not change. We don't know how to solve this functional form yet, but if we can solve this functional form, doing multiple parameters is no harder than doing single parameters. Just like linear regression, multiple linear regression, both were exactly similar conceptually. This entire thing gives you a value of probability that new person that you are going to find is going to be in this class or that class. That's what we are trying to fit. We are ultimately fitting probability. Since we don't know a function that can give you these discrete values, we interpret this as probability, and probability has continuous values. So when the probability value turns out to be less than 0.5, we can say that that guy is going to be in that class. When the probability value turns out to be, less than 0.5 is going to be in this class, greater than 0.5 is going to be in the other class. Okay. So this functional form, what it does in this, what it gives you in this case is probability. We'll come there. We'll come to those edge situations in a bit, because there is no, we don't even know whether 0.5 is the right threshold to use. It just happens that the convention is at 0.5 we always round it to 1, as you know from our rounding thing. So that's it. But typically what you would try to do is you would try to move the value of threshold and see which side it would, whether it would matter dramatically one way or the other. So we are now going to see how do we fit this complicated functional form to a given data, right? Before I do that, I want to introduce to you a term that is commonly used in betting, gambling, odds ratio. Are you guys familiar with this term? I mean, it's odd to ask this in India, given that gambling is illegal. It's like asking people like, which one of you have shoplifted? Nobody's going to raise their hand, right? So it's okay if you are familiar with the term. What this term actually does, odds ratio, is the ratio of winning, probability of win to probability of loss. That ratio is called as odds ratio. That is the term that you would encounter whenever you watch soccer games. Soccer games, they talk about, the odds of this team winning is 3. What they really mean when they say odds are 3 is that the probability of the win to loss is 3. So they have a 3 times higher chance of winning than losing. That's what the odds ratio means. Um, so if the, let's see if we understand this ratio. If the probability of winning is 6 by 12, what are the odds of winning? Half 1. Odds is probability of win to probability of loss. Probability of win is 1/2. So which means probability of loss is also 1/2. So odds is just 1. 1 is to 1. If the odds of winning are 13 is to 2, what is the probability of winning? Sorry? 13 by 15. So look at this. This is the ratio of win to loss. Right? So what, in order to, so this portion corresponds to the win part. Right? This 13 corresponds to win. But we want to compute probability. Probability cannot be greater than 1. Right? So it's what it truly is 13 divided by 13 plus 2. Okay, the probability of winning therefore is 13 by 15. If the odds of winning are 3 is to 8, what is the probability of losing? 8 by? If the probability of losing is 6 by 8, what are the odds of winning? Probability of losing is 6 by 8. So odds of winning are, what's the probability of winning? 2 by 8. So the ratio between these two is going to be 2 is to 6. So as I mentioned, whenever when you watch foreign telecasts of any of these games, they automatically give you these odds in different things. So now you know what those odds mean. Odds are nothing but the ratio of probability of winning to probability of losing. Right? So why am I introducing you this? The odds ratio is nothing but probability of win divided by probability of loss. Right? Now in this formula, I'm going to substitute that big massive formula for the logistic equation. Okay, the sigmoid curve. Right? I'm going to substitute that particular formula over there. Thing is, it simplifies nicely into this. S is e to the power beta naught plus beta 1x plus beta 2x2, so on. It's still a nonlinear equation, still an exponential equation. But do you know how to convert this exponential equation to linear? Log. So instead of dealing with S, the odds, if you deal with log of odds becomes a linear equation. And we know how to handle linear equations. Right? So we have managed to reduce the complicated sigmoid curve for the probability to a linear equation in terms of log odds. And what the logistic regression command, what that formalism does is converts that into log of odds and estimates the value of parameters that's most likely to fit your given data. Okay, so idea is exactly same. We like linear. We are trying to find the kind of transformation that will convert the given nonlinear pattern into linear. Okay, so the log of odds ratio is called as logit, and the transform model, therefore, in terms of logits, is linear in the data. Okay, the way we evaluate the given that data set, the way we compute the coefficients is using the command glm. LM was for the linear model. Linear model, it's computed using the least squares fit. what we do for trying to solve for this logistic regression is we use the generalized linear model. Okay, that's where the GLM comes from. And so you give, the formula, the input that you give is the zeros or one corresponding to whether the person is going to respond or not, right? You want that as a function of age, right? So response as a function of age is what you're trying to do. But in this command GLM, you also have to explicitly state that this guy, this response is a digital quantity. It's got only two values, not multiple values. So you say family is binomial. Okay, this is where you're telling that you're dealing with trying to forecast a class variable and not a numerical number. Okay? So when you say family is binomial and you send that to GLM, it automatically knows you're trying to do logistic regression. And the output looks very similar to the output that you saw in the case of linear regression. Is the model significant? Not the model. Is the coefficient significant? The coefficient significant is you have these 3 stars. So both these coefficients are significant, right? At significant at 0.1% significance level, right? The difference between what we did, there is some differences between linear model that we did there and this generalized linear model, is that in the output that comes later on, instead of seeing R squared values, you see AIC values that are displayed. R squared is not at all displayed here. We'll talk about that in a second. But these two are significant, right? What will be the equation? Minus 20.407 plus 0.425 times age. That's equal to what? Sorry? Log of odds. So the equation is log of odds is that. Okay. Let's, how does this data actually look? This was the data we said. The fit, once you give those parameters and convert that back into probability, take the log odds and convert that back into probability, the fit looks like this. Okay, for that particular data set. The line that I've drawn here is a line that's corresponding to the 0.5 probability line. So we said that the probability line is where 0.5 is where this exponent was 0, right? This exponent is basically the equation that was there in this equation. That is this guy. That exponent was what we simplified into log of odds, right? So when that exponent is 0, I can just set that equation to be equal to 0 and compute the place where you have this 0.5 probability. Log of odds equation was this. I set this number to 0 and I can solve the age which will give me the 0.5 probability. So if you choose 0.5 as your threshold, that would imply that anyone who's got an age that is less than this would fall into this class. Anyone who's got an age that is greater than this would fall into the upper class. Okay. Now, 0.5 threshold is not a given. It depends on the business. The business owner will decide what is the level of threshold he will choose based on how much budget he has, how many people can he send the flyers to, right? It does not mean that when someone's probability is less than, let's say someone's probability is 0.3, it does not mean that he's not going to return the flyer at all. There are people who in that range who have returned the flyers. It says the probability of that guy returning the flyer is small. Over here, the probability of that guy returning the flyer is high. So zero point 0.5 is an arbitrary threshold that's chosen by the business owner, depending on how much budget he has, how many flyers he can sell. So the model itself automatically does not suggest the threshold. We will later talk about how one may choose the threshold and so on. But given this threshold, this is the way you compute which is that particular point, which will separate you from one class versus the other. Correct. More greater than 50% probability he will sell. And below that, it's less than 50% probability that he will return. Yeah. Um, so, so yeah, this 47.9 is that. Okay. Suppose we want a probability that a 50-year-old club member will return the form. What do? We have this equation, logistic equation. All I'm going to do is substitute age is equal to 50. The number that I get is the log of odds. That is not the probability. The number I get is log of odds. So log of S is 0.89. Therefore, S would be 2.435. Odds is 2.435. How do I convert this to probability? So this is really 2.435 is to 1. Right? That's the odd. So probability of win would be 2.435 plus 1, 2.435 divided by 2.435 plus 1. Right? So that's what it is. The probability turns out to be around 70%. So probability a 50-year-old will return the form is 70% based on this particular model. Okay. So if you use the 0.5 as a threshold, then you would classify him into the 1 class rather than on the 0 class. The same thing you would evaluate using R the following way. So you use this command GLM to fit this data, response to age as a function of age, and you're explicitly stating that the family is binomial. This is the command you use to fit that. You send the output to flyer response. Okay. You want to evaluate the probability of a 50-year-old returning. So what you do is you put this 50-year-old into a data frame called ND, new data. Then you use the predict command. This is exactly the way you work with linear models too. When you want to predict something, you use the predict command. So you say predict for this model where the new data is ND. That's the command you do. The output it gives is 0.89. This is the log of odds. Okay. But you can also ask it to predict directly the probability. So you say type is response. If you add that, then it will give you probability. In this case, it's 70%. Okay. So this is the way you handle logistic regression. Why don't we take a 5-minute break and then we can come back and talk about how to interpret those other numbers that came out of R. We'll get there. Do ask me the question. No, we'll get there. Coefficient will not be there. If your input rows are perfectly correlated, it will give NA as value of coefficient.
Type and one count. Remaining the dummy variable. So I need to predict the count with type. So I'm not getting.
It should give. You can, if you show me the thing, then it should not be hard to debug.